All right. Well, I hope people are remembering that spring break has ended. It's hard to say. We still got about 8 more minutes. So I am going to see if there are questions. If so, I will try to answer those questions before class. This is officially my office hour too, so you guys can ask questions about the class. Alright, so what we are seeing here. Oh, okay. I'm not sure about that. I didn't really get much of a break. I was frantically grading every day. So during the day, I got my yard to clean up because there's work to be done. And then in the evening, after working in the yard for a whole day, I get to uh, grade the exams. So so right now we are in the final approach to the final exams. As you can see here, the final week is from the 12th to the 18th. And before somebody asks, so when is our final exam? I'm gonna let you guys think about it for a little bit and see if you can find it yourself. Just like everything else in this class, right? Yep. So you gotta be putting some effort to try to find it. And for some strange reason, our spring break always coincides with Easter. Um, and Easter is a very interesting holiday because its timing or the date of Easter depends on a few things. It depends on the phase of the moon, the calendar, and I think that's one more thing. Day of the week too. I think there are like a few things to determine the date of Easter, which traces its root from the pagan holiday. I mean, therefore we get Easter eggs and bunnies. Because pagans are much more aligned with the moon cycle compared to the sun cycle, so that's partially why that's Easter is a strange holiday to determine what date it's going to fall onto. All right, looks like we are getting a lot more people getting in. I think as an assignment, even though it's not going to be politically correct, but as an assignment, it'll be kind of fun to just have people to write an algorithm to determine when Easter is given a specific year. And it's it's harder than you think. It's much harder than you think. All right, I'm not seeing anything in the text channel. I think most people are probably still in spring break mode. I'm getting maybe 10 people on Discord right now. That's about less than one half of the class. And then on the YouTube side, I have one person viewing. All right. I guess some people may have realized it doesn't make any point. It doesn't make any sense to take roll anymore because the last day for me to drop people and the last day for people to withdraw from the class was yesterday. So that day has passed. All right, 3 more minutes. So if you guys have any questions to ask before the class, now is a good time. And I am just counting the days, not because I don't want to. I want this semester to end. In fact, it is quite the opposite. I want the semester to have at least 2 more weeks in order to cover all the material that I really should be covering. Unfortunately, I cannot do that. The school won't let me do it. And then I have here about cases where a professor, of a certain class in a certain campus decided, hey, I got nothing else to teach now. So what am I going to do with the next 4 weeks? Oh, I know what to do. I'll just tell my students there won't be any classes anymore, and I'm going to give you guys all good grades, so don't tell the dean about this. That actually happened. All right. I cannot imagine, how anyone can teach this class, within a 16-week semester because there's just really too much material to go over everything. So yeah, some people were actually okay with it. I mean, the professor said, "I'm going to give you good grades and just kind of let's end the semester a little bit earlier." I suppose it depends on what kind of a class it is. I mean, if it's a class where it's just a formality, to get your degree, I suppose, it's still not good. But if it is one of your major, if it's a class, from your major, then it's a different story. I mean, as useless as this class may seem, not exactly the content, but the thinking process, that we use in this class can still be very useful in, just, programming, generally speaking. I think in English, the difficulty is what is the grading criteria, right? What are they using to assign a grade? Is it really the mechanical part of writing, or is it the content that you're writing, or whether you are writing something that the professor agrees with? I mean, that is not supposed to be a part of your grade, but I suppose some people may grade it that way. Good thing I'm not an English professor. I cannot be an English professor. That would drive me insane. All right, so I am gonna get started. It is noontime, and yeah. So regarding the text traffic in Discord, I do have one thing to mention. One thing I think many people may not realize is a community college is a good place to try to figure out whether a major is suitable or not. I know it. I know how it sounds, and I know how it. What people may think is my intention, but I assure you that is not my intention. Um, it's just that I have seen cases. I have seen examples where people who changed their major became happier and more successful compared to before they changed their major. So, all right, so I'm not going to use up much class time to talk about that because, as you can probably imagine, we are kind of trying to get all the things through in this class. All right, so the final exams are from May 12th to 18th. Since this is a fully synchronous class, we follow the final exam schedule that can also be found at the ARC website. I believe Chris has already figured that out and put it into the general text channel, so you guys can go there. Or you can look it up, just look for American River College final exam schedule. And based on the start time of the lecture, this class doesn't have a lab, so there's no confusion there. So just based on the start time of the lecture, you can find the date as well as the time for our final exam. Alright, so as we get close, I would definitely remind you what day and what time it is. But for now, I think I want you guys to try to look for that yourselves. Alright, getting back to what we're going to talk about today. There were some questions about question 8 of exam 1 pi, which I graded over the break, or I cannot remember when I graded it, but it was graded. So that's a very good example of what I would call a very minor twist from question number 8 of the original exam 1. And the intention was simple. I was too lazy. Okay, I was just simply too lazy to think of another question, because there are only so many things you can ask about the g function. And so this is from my own example. So it's basically asking, how do we utilize the g function or the value of the g function of pixel 3722 and use that and combine with some addition and subtraction to find out what is the g value or the value of the g function applied to the pixel 3823. So that's basically the essence of the question, which then later on it was generalized to 37 is just called x, 22 is just called y, and then the 36 is just x minus 1, and then the 23 is y plus 1. So instead of answering that question directly, not even now, I'm going to ask these questions so you guys can think about it. Okay, how does the pixel 3722 relate to the pixel at 3623? In other words, think in terms of the diagonal lines. Okay, so in that context, how do these two pixels relate to each other based on how natural numbers are assigned to these so-called pixels? And then from there, you can go ahead and try to figure out this example. Once you get to the g value of 3722, how do you figure out the g value of 3623 without using multiplication, division, and all those complicated operators? Instead, I'll just give you a clue. Add 1 or subtract 1. Which one is it? Why? Okay, so that's going to be my question to those of you who asked what is the correct answer of question number 8. Yes, so that's it for question number 8. So now we're going to go back to the present, and this is a hyperlink that you guys obviously cannot click, but that's okay because I'm going to copy it and paste it to the text channel. So now you can also click on that link. So what we're going to do is continue to talk about the two functions that I kept talking about. Yeah, I'm going to give you an example of how to do it, but I never really got enough time to do it until now. Yeah, I'll go ahead and do it. I still have exam 1 itself to grade too. That one has not been graded or scored, so I still have to do that because I promised that I would use the highest or the maximum between 1 and 1 pi in the system. So that's why I have to grade that one too. Even though most people probably did a lot better in 1 pi compared to 1, but since I said we'll take the maximum, I'm gonna have to grade the first one too. However, you can probably figure out your own score, at least based on everything that has been graded already, because the first exam, whether it is coming from 1 pi or 1 itself, is 20% of your final grade. The second exam is also 20% of your final grade, and then the assignments, all of them added up, is also 20% of your final grade. Oh, okay, well, thank you. I'm still gonna go through it just to make sure, right? That's otherwise I would not be responsible. I mean, being late and it's not responsible, but I still want to make sure. Anyway, so there is that. All right, so we have quite a few more modules to go over before the end of the semester. So what we'll do now is to get back to counting, and we are going to focus on. I'm going to use section 7 as an example because I think section 6 is very similar. It's actually a little bit easier. Let me see. Yeah, so section 6 is a little bit easier. Section 7 is a little bit harder. So we'll go ahead and go with section 7. All right, so section 7 is about a function that will generate all the combination outcomes of an experiment. So we are no longer just doing the counting. The counting is easy, okay? Once we have combination, as a function that returns an integer, and once we have permutation, it's doing the same thing except it returns the number of permutations. That's pretty easy to do, okay? We just have to use factorial and division and multiplication to get it done. So what sections 6 and 7 are doing is no longer just counting. It is actually generating the outcomes. Section 6 generates the outcome set of experiments with permutations, which means ordering is important. And then section 7 is doing the same thing, except it's generating combinations where ordering is not important. So the way this is done is it is recursive. So we'll go ahead and take a look at the notation. Let U subscript I of x represent the set of all possible combination outcomes of an experiment, with I trials, and the set x represents the set of choices available to the first trial. Okay, so do we have any questions about this notation? U subscript I of x, x being a set. So we'll start with that first. Okay, we'll make sure that we understand that concept first. Are there any questions about what's an outcome? What is an experiment? What is a trial? And what do we mean by choices available to the first trial? What is with replacement and what is without replacement? Those are all the concepts that we have talked about before, but it was a while back, like 2 weeks back. So just want to make sure that we are all on the same page as we speak. And I'm not referring to the URL either when I said we are all on the same page. All right, so we got a few people typing. All right, so we are good. I'm guessing that yes, we're good to go. And then can I just explain U0x notation with a simple example like coin flip? Okay. Coin flip would not be an experiment that is without replacement, because once you have a coin that lands on the head, it can land on the head again. So that means we are looking at taking things out of a bag. Okay, that's more like it. Yeah, so we are basically taking, say, marbles out of a bag. So you label the marbles 1, 2, 3, 4, 5, put all 5 marbles in a bag, and then you take one marble out of the bag at a time, and you don't put it back into the bag, during the experiment. So that's why it's called without replacement, because once you take something out of the bag, that becomes the outcome of a single trial, but that possibility is no longer available for all the subsequent trials. And each trial is basically taking one marble out of the bag. So is that okay? Does that kind of explain, put all the terms in context? And then the I is basically saying how many marbles are we going to take out of the bag? And combination means I don't really care about the order. So whether you take the marbles, let's say labeled 1, 2, and 3 out of the bag in the order of 1, 2, and 3, 2, 3, and 1, 3, 1, and then the 2, it doesn't matter. Okay, as long as you end up with the combination of the marble labeled 1, 2, and 3, they're all considered the same outcome. So that's what the combination means. So are we good so far with those terms? Getting reacquainted with the terms. Okay, Excellent. All right, so we're going to start with the base case, okay, because this is a recursive algorithm. So when you're trying to understand a recursive algorithm, you can use whatever means you want to use, okay? But when I look at a recursive algorithm, I always look at the base case first. In other words, when do we stop the recursion? I always look at that first, because that tells me, okay, so this is how we stop. Okay, this is how we stop calling the subroutine itself or using the definition again, and that is usually very important, at least when I try to understand an algorithm. So U0 of x means we are looking at a weird experiment that has 0 steps. Okay, so you can kind of imagine x is a bag of marbles again, okay, and each marble is distinct. Now, how do we know each marble is distinct? Because it is a set, right? Because in a set, all elements have to be unique. They have to be distinct from each other. Okay, so we are looking at a bag of marbles that are distinct from each other. And the 0 means I am conducting an experiment, a weird one, where it has 0 steps. Okay, so you can kind of imagine that you have 2 bags. Okay, one bag is where you take the marbles from, and then the other bag is where you store the marbles that you have taken out of the first bag. So kind of have that mental picture, right? So in this particular experiment, let's just say that x has 1, 2, 3, 4, 5. Okay, just as an example. So by the time we finish with this example, with this experiment, what would be in your bag, in your personal bag, the bag that is supposed to store the marbles that you have taken out of the original bag? And here's the question, right? This is how we understand the base case. 0 trials, we're talking about U of 0 of x. X being 1, 2, 3, 4, 5. 0 means, we have a weird experiment where there are 0 trials. Then 0 in our bag. Not exactly, that's not how I would describe it. I think I understand what Danny means. Your bag is empty, right? Because, you did not take anything out of the original bag that has 1, 2, 3, 4, 5. So by the time this experiment ended, that bag still has excuse me, 1, 2, 3, 4, 5, but your bag is empty because you did not do one single step to take anything out of the bag that has 1, 2, 3, 4, 5. Exactly. So Luke is correct. Excuse me. So that's why your outcome set is an empty set. Then people would be asking, but is this a typo? Because it's an empty set within a set. The answer is it is not a typo. Excuse me, I'm going to turn off the mic when I cough a little. So this is not a typo because remember this set here, the outer braces, is a set of outcomes. And the inner empty set is basically saying the only outcome is an empty set. The only thing you can get out in this case, in this particular experiment, is you end up with an empty bag. So this is important. It is very important to understand why we have a set. The outer set, or the U function itself, is not an empty set. It is a set that contains the empty set itself. So is that explanation okay? I mean, does everybody understand? Because having your bag being empty is one of the outcomes. Technically, it is one of the outcomes, even though in this case it is the only outcome, but it is one of the outcomes. All right, so I'm just gonna. Okay, so is that outcome always the case with all experiments, or is it case by case? Well, it depends on what you mean by case by case. It is regardless of which. I mean, if you look at this, do you think the right hand side depends on what x is? Let me just look at it. Does the right hand side of the equality mentions anything about x? If it does not, that means regardless of what x is, as long as you have 0 trials, you always end up with an outcome set that contains just the empty set itself. No. So u1 of x is not the set of 1, 2, 3, 4, 5. It will be the set of 1, and then the set of 2, and then the set of 3, and then the set of 4, and then the set of 5. Because those are the 5 possible ways for you to end up with your whatever is in your bag, right? You can draw the marble labeled 1 and put it into your bag. That's one outcome. Or restarting the entire experiment. Okay, this time you took out the ball or the marble that was labeled 2 and then put it in your bag. That's your second possible outcome, and so on. All right. So so instead of just trying to understand this in an intuitive way, we're going to do it in a very non-intuitive way. In other words, now that we know what u0 of x looks like, let's think about what ui of x is going to look like. All right, so this is where it is kind of important to kind of use a simpler case. 5 is too much. So we're going to use 3 instead. Okay, so we're going to have, the original bag of marble is going to have 1, 2, and 3. And we're going to have 2 trials. So let me go back to my notes here. There we go. And so I will type up the exact scenario that we are going to look at. Okay, so original problem is to try to figure out what is u underscore 2 of the set that has 1 and 2 in it. Oh, 1, 2, and 3. Sorry, there were. You can have more elements in the set than there are steps in the experiment, but not the other way around. So the question is, how do we figure this out? But as I said, I'm not going to do it in the more traditional way, which is to trace or track through the recursive call. So I'm going to do it in the opposite way, which is to do it from a bottom-up approach. So the bottom-up approach is basically saying, okay, so when we get all the way to the end, when the recursion ends, which means we're looking at u0, it doesn't matter what it is, okay? But we know that when we get down to u of 0, the set still has one thing in it, okay? So we'll say, what if it has 1 in it? It doesn't matter. Tag you just said earlier, it would make a difference. Okay, so when we look at u0 of 1, the set of 1, the outcome set is going to be an empty set. Because this is corresponding to when there's only 1 marble left in the bag that I'm asking you to draw a marble from, and I'm telling you don't draw anything from the bag. So what is going to be ending up in your bag? Nothing, right? I mean, so that's nothing. No. U5 of x. Oh wait, hold on a second. So u5 of x is going to be a set with a single set in it, and 1, 2, 3, 4, 5 would all be in that set. So so Dalton is correct. So Dalton is correct that the question that Danny is asking in the text channel, the answer, which is to the right hand side of the equal sign, would actually match if the left hand side was u underscore 5 of the set of 1, 2, 3, 4, 5. So Dalton is correct in that case. So let me just kind of reply there and make sure that we understand that. All right. Because what that means is, you have a so let's just look at it this way, from the symbolic perspective. Okay, so let me get back my cursor, get back here. Oh, no, not this one, but this one here. Okay, so if you think about this x as a bag that I am presenting to you, and then the answer or the outcome of the function to be what is in your bag, right? What can be the scenarios of what ends up in your bag. Okay, so u5 of the set of 1, 2, 3, 4, 5 means I am putting 1, 2, 3, 4, 5 in a bag, and I present that bag to you, and I'm asking you and say, Okay, perform 5 steps. Each step is taking one marble out of the bag without replacement and put that marble into your own bag. So the question is how many ways can you draw marbles out of the bag? In other words, how many possibilities do you have of regarding what ends up in your bag? There's only one possibility because you're going to draw all 5 marbles into your bag. The ordering may be different. You may draw it as 1, 2, 3, 4, 5. You may draw it as 1, 2, 3, 5, 4. You may draw it as 5, 4, 3, 2, 1, and so on. But it doesn't matter because we are looking at combinations where the ordering is not important. Okay, so that hopefully that explains Dalton's response to Danny's question. All right. Okay, so we got some off-topic text channel stuff which I am going to ignore for the time being. All right, so hopefully that kind of answers that specific question. So we're gonna have 3 of these. Okay, so we have this one, we have this one, and then we're gonna have this one too. So you guys may be asking, but why only focus on these 3? Because it doesn't matter what is in the set. Okay, what is inside the braces here doesn't really matter because it always ends up with an empty set. But yet I'm only including these 3. Okay. Well, that really has to do with the original problem. Okay, so the next thing I need to figure out is U1 of something. So that becomes a little bit more interesting because it is no longer by definition. So when I want to look at U1 of something, that set is going to have 2 elements now. Okay, so one way is this one way is this one, and then the last way is going to be this one here, and obviously the right hand side is incorrect in this case, so we'll try to find out what should be on the right hand side. Okay, that didn't work. That worked. I'm just experimenting with VI commands. Oops, nope. DT $, and the rendering software doesn't like to have that extra space, so it stops rendering when there's an extra space before the $. Okay, so we'll try to figure out U1, 1, 2 of something. And now some of you can look at this and go like, oh, that's easy because U1 means we are looking at experiments with only one step, right? And this time we start off with a bag that has a marble labeled 1 and a marble that's labeled 2, and you're supposed to only draw 1 marble out of the bag at a time, and that's the entire experiment. And I'm asking, so what are the possible outcomes? So you guys go like, oh, that's easy because it's just this exactly what Danny typed in the text channel. Okay, so the outcome set is supposed to be a set of 2 elements. The first element is the set of 1 itself, and then the second element is the set of only 2 by itself. That is correct. But intuition can only go so far. Okay, intuition is good. It's good when you're trying to understand what the problem is trying to solve, or what you're trying to solve. What is the nature of the problem. But what we want to do is to generalize from what we see as an intuitive answer into a formal way so that we can apply that logic to more cases. We're trying to generalize the approach. So to get back to the notes here, so now we are looking at not the base case because we're no longer looking at U of 0 of something. So now we're looking at the general case, which is UIX of something, and then we have this gigantic mess here. Okay, so maybe I should just kind of magnify that a little bit because it does get a little bit harder to see the subscript without the extra magnification. All right. So we look at this and go like, but Tack, I have no idea what this means. Well, if anyone is thinking that, that's okay. You don't have to admit you're thinking it. If anyone is thinking about that, then my only suggestion is, well, take it one step at a time. One step at a time. So the question is, what is x? Well, x is pretty easy to figure out because in our example, x is 1, 2 in the set for the first test case, 1, 3 in the second one, and 2, 3 in the third one. Okay, so we now know what x looks like. Then what about this symbol over here? Okay, big U and then E of something. Well, what that means is we are now going through a loop. And the loop is each iteration of the loop is generating a value, which is this part here. And then for each value that each iteration of the loop is generating, we take all of those and then we perform a gigantic union between all of those things. That's what the big U notation is trying to say, is we are just taking for each iteration, generate something out of E as an element of X, and then take that thing and then we just make a gigantic union of everything. Is that understood, or do you guys want me to kind of explain that in a pseudocode fashion? Okay, so I'm going to take it as let's look at the pseudocode, right? All right, so let's go ahead and take a look at the pseudocode. All right, so I'm going to put the pseudocode down here. All right, so this is how the pseudocode is going to look like, and we are going to say let x is being a new set, and the set is initialized to, I don't know, 1, 2, 3, 4, 5. Okay, so this is just an example. Okay, this is not corresponding to the example that we are trying to solve. I'm just giving you an idea of how JavaScript can work in this case. All right, so next what we want to do is to say, okay, so now we want to look at the notation, what we're trying to solve, right? So we'll go ahead and say what is big U subscript, and then in here we say E in X, and we'll do something fairly simple here. Okay, we'll just go ahead and say we'll just union E itself. Okay, or whatever f of E is. There we go. That's better. So that makes it more general. Okay. So I'm using the same notation. I'm using the same notation as in the notes here. I'm using the same big U E of X, except this part here gets a lot simpler. Instead of this gigantic mess here, I'm just saying, okay, let's not take the entire mess. We'll just call it f of E. F is some kind of function that returns a set. Okay, it has to return a set because otherwise we cannot perform unions. So now that we are given that, we can continue to talk about what this is actually going to do. So we'll say let result be a new empty set. And then what we'll do is to say for let E in X. Okay. Not sure whether that's going to work or not. Let me just look up, because I do want to give you the correct syntax in JavaScript. So we'll say for in JavaScript set and see if that works. I'm just looking this stuff on the side. Oh, it's going to be of, not in, because in only works when we are working with members inside an object. So for both array elements and also set elements, it is actually the word of. All right. So now we're going to say let iteration result be f of e, whatever that is, and then the result is just going to be unioned with that thing. So result is going to be result dot union with iteration result here. Now, by the way, union is not actually a method using the JavaScript set notation, but you can implement your own union and intersection and whatnot. So that is basically what the big U notation is trying to do, is to say, okay, here is a set X, and we are going through every single element of X, and then for whatever element we are focusing on, for each iteration of this loop, we use f of e to give us another set. Now, f of e can be something simple, can be just e by itself, right? It can be just the empty set, or it can be something far more complex. We don't care, okay? Whatever that thing is supposed to be a set. So that set is now stored in the local variable that we call iteration result, because it is the result of a single iteration of the loop. And what we do is we basically look at result, which is the running union of everything, which is the final result that we want. And we want it to be unioned with whatever this iteration is producing as its own set. And by the time we get out of the loop, result is going to be whatever this expression is going to return when we apply that in notations like this. So is that okay? Does that kind of help or not? All right, so let me get back to the text channel. Pseudocode would be cool. So is that helping, Dalton or Luke? How about Danny? All right, cool. So it doesn't quite work, okay? If you type this in JavaScript, it doesn't work because a union is not actually a method of the built-in set. So you kind of have to extend a set a little bit to implement your own union method, but that's the general idea. Alrighty. Okay, gotcha. All right, so now that we understand what is the big U notation, now we go into the mess, okay? So now we understand what this big U thing is trying to do. It's basically, all it's trying to say is go through everything in the set X, and then for each element we're going through, generate something that is supposed to be a set, and then we make a gigantic union of those things. That's what this portion is trying to say. So now our focus is shifting to f of e, which is this mess over here. Oh, okay, cool. All right, so now we go through the other side, which is this notation here. And once again, it is a headache, right? It's like, what is this doing, okay? So the first thing is to parse this expression and figure out which part is which part first. So once again, we have a big U notation, and every time we have a big U notation, we have to say, okay, so which set are we going through, okay? And then what variable is being used to represent the variable that gives us the what we need to work with per iteration. So in this case, big uppercase S is the name of the per iteration variable, and it's coming from U big UI minus 1 of X minus E. Okay, so now let's take a look at this thing here. Well, recursion works only because how I choose to look at things. Maybe I should address that first. Okay, so that's gonna break our attention span, because we were just kind of on our way to explain this portion here. But I think it is actually important to understand how recursion works in this case. Okay, so let me give you the same 3 marbles in a bag example. Okay, no, it's fine. It's not a problem. All right, so what we want to do, because I think this is actually important, maybe more important than the mechanical aspect of it. Okay, so what we want to do is to take a look at so without referring to the algorithm, let's just kind of think about this from a logical perspective, from a human intuitive perspective. Okay, so let's just say that this is what we want to figure out. Okay, this is what we want to figure out, which is big U of, let's say, 2, and then we have 1, 2, 3, 4, 5 in it. Okay, so this is what we want to figure out. Okay, we have, so my bag that I let you choose marbles out of has 5 marbles. They are labeled 1, 2, 3, 4, 5, and I want you to pick 2 marbles out of the bag. Now, obviously, most of you already know what the solution is going to look like, but what we want to do is to look at it from the perspective of recursion. Okay, so in this case, okay, so I'm gonna break it up. So I'm going to use a bulleted list. There we go. All right, so we're going to look at this and say, if I choose, okay, so if the first element, which we'll just call E, turns out to be 1, then what are we going to do? Okay, so we have 5 cases, right? Because there are 5 possible marbles you can choose out of the bag, because you can choose the marble labeled 1 as the first marble that you take out of the bag, or 2, or 3, or 4, or 5. Is that okay? So this indentation level, okay, this indentation level here is basically saying, of the 2 trials, the first one can choose 1, 2, 3, or 5. Is that okay? Does everybody understand the notation here? All right, cool. So now, if the first marble that you took out of the bag was indeed the marble labeled 1, then what is the subproblem? How many trials are left? Well, let's see. Well, since you were only allowed 2 trials, which means you're only allowed to take 2 marbles out of the bag, you have taken 1 already, so you have 1 marble left to take out of the bag, right? So that means, and how many trials have we left? We have U1, because there's only 1 trial left. Of the 2 trials total that you are allowed, you have used 1 trial already, so you only have 1 trial left. But with this trial left over, what are the choices that you can get out of the bag? Well, you took the one labeled 1 already out of the bag, so the only ones left in the bag are the ones labeled from 2 to 5. So this becomes your sub-problem to solve. Okay, I mistyped here, $, there we go. So do you see why, when E is 1, if the first trial is taking out the marble labeled 1, then you have a sub-problem of, 1 trial left, but whatever you can choose for that second trial can not be E anymore. It has to be the original set, which is this one here, minus whatever E is. Is that okay? Are you guys kind of getting the idea? Now I can take this, okay, I know this is going to be a little bit on the tedious side, but I think it might help some people kind of gel the concept. So with this one, you only have 1, 3, 4, 5 left, because you chose to you took the marble labeled 2 as the first thing you took out of the bag. Okay, so with this one, 3 is not a choice, but guess what? 2 is back here. And then with the last one, 4 is not a choice, but 3 is a choice in this case. So, and there's one more, so might as well, since I'm here already. So with this one, you only got 1, 2, 3, and 4 here. Okay, so now you look at U1 of 2, 3, 4, 5, and you apply the same thing. So the question is, when we look at this, we go like, okay, I totally get this one, because I can see a bag with exactly 5 marbles, and I can understand what I'm supposed to do. I'm supposed to take 2 marbles out of the bag without replacement. So once I take something out, I cannot put it back into the bag. And we're just trying to figure out, how many ways can you take 2 marbles out of this bag that had 5 marbles to begin with. In other words, what are the possibilities of what ends up in your bag, and ordering is not important. Okay, that was it, right? So we can totally look at this and go like, yes, I can feel those marbles in the bag. So now the question is, how do we turn this into a more general logic? Okay, so I think this part is really important. Even though I'm supposed to teach discrete math or discrete structure, this has to do with programming. This has to do with how you think about a problem in order to formulate a solution. Okay, because we're trying to generalize now. Okay, we looking at this and we understand this particular example. So the first thing we generalize is we say, okay, what about we don't say anything about what set we begin with. Okay, we just call it x. Okay, okay. So if that is the case, and we are not going to say what marble you're going to take out, we just say, okay, the marble you're taking out of x is called e, or it is stored in variable e. All right, so what are we going to do here? I guess that's not available anymore, so we can no longer use x here, even though it's a good starting point, but we cannot do that. We have to make sure that e is not one of those choices anymore, because e is used already in this trial. Are we still doing okay so far? In terms of generalizing from the from the concrete example to the symbols. Oh, I forgot about the the braces need to be escaped. Okay, give me a second here. There we go. All right, cool. So now the other ones, we have to remove, right? Because they don't make sense anymore. Because since we don't know what is in x, we can't really say, oh, here are the other things in x. No, we have no idea what are those other things in x. So we can only say that we can only say for each e in x, right? That's all we can say, because we really have no idea what is in x. We just know that, well, assuming it's not empty, because if x is empty at this point, we have a bigger problem. Because tech, you told me to take more things out of the original bag than there were things in the original bag. Tech, you tricked me. That would not be a good thing. Okay, so now we have to deal with the 2 versus the 1, right? We're trying to generalize. So instead of saying, okay, in concrete terms, you're supposed to take 2 things out of the bag. Now that you have taken 1 thing out of the bag, how many more things can you take out of the bag? Okay, I should point here. So instead of saying, originally you were allowed to take 2 things out of the bag. Now that you took 1 out of the bag, you can only take 1 more out of the bag. We also generalize that. Okay, so instead of using 2, we say, we'll just call it I. Okay, so I is now a term, a variable representing how many things you were originally allowed to take out of the bag. Now that you have taken e out of the bag, 1 thing out of the bag, guess what? You only have I minus 1 thing trials left. So are we starting to see how the recursive definition was formulated? I think that really is the important part, because once you understand how the recursive definition was formulated from the beginning, then the rest is mechanical. The rest is really just going, oh, okay, so mechanically we have to do this, and then do this, and then do this, and then do this. All right, so I'm getting a bunch of yeses here. So now the last question is, what if when do we stop? Right? The next question is, when do we stop? Well, the time when we stop is when I equals to 0, because when I equals to 0, then there's nothing left. Okay, you have no more steps left, and then you end up with a bag that is empty for that subcase, and then you have to take that back and then look at this thing here. So this is not quite the entire solution yet. Okay, so we're gonna say we'll give this thing a term here, and let's see, what term should I use? I just need to make a unique term that has an index of e. Oh, I know what to do. This is f of e equals to that. Okay, So f of e is really just a short form of this thing here. Now it's supposed to also have e and I and also x, as its parameter, but we'll just kind of simplify to e here. All right. So now, so for each iteration, we collect one thing called f of e here. So now the question is, once we have generated all of these results, what are we supposed to do? Well, it's not just to take a union of all of those things, okay? Because f of e is not by itself a solution of ui of x. It is a part of one part of the solution of ui of x. So when this is all done, then we get out of the algorithm, and then we basically have to say u of I, okay, the answer to u of I, oops, subscript I of x is as follows. So what we need to do is to take each f of e that we generated up here and say, guess what? That thing needs to be unioned with e itself to make an outcome from the perspective of ui of x. So we basically say, I'm going to switch to pseudocode here. Okay, so we have pseudocode. So what we need to do is to say for let uix, okay, result of uix be a set first. Okay, so initially it is just an empty set. And then what we do, oh, okay, I cannot type today. And that's because my there's an injury on my finger. Well, not exactly an injury, but I have to put a band-aid over it. And then what we need to do is to say for e of x, do the following. uix is going to be uix union with. Well, what are we going to union with? Well, it turns out to be e as an element. We have to generate a set out of it, and that has to be unioned with f of e. So let me type it first, and then I'll explain what that means. Okay, so I'm gonna break up those lines. And you might say, but Tech, this is a weird way of formatting parameters of a function call. Well, if you program in JavaScript, you're going to do this a lot, because you can pass an anonymous function, which can then contain its own anonymous function that can also contain its own anonymous function, and so on. So things can nest in a very nasty way when you program it in that particular way. So anyhow, so this one is going to be a new set of e. So I'm generating a set that only has e as an element in it. But this is not the result, okay? So this thing is a set, which means it's supposed to have a union method. And it has to be unioned with what we generated earlier, which is f of e. So we're going to just refer to it as f of e here. All right, so why are we doing this, right? Why are we having to union the whole thing? Well, from the perspective of ui of x, e is actually a part of a combination. When we look at it from the perspective of you have I trials left, and x is the available choices that you have. So e is a part of the solution. But e also has to be unioned with the result of the subproblem. The subproblem is, once you have taken e out of the bag, what is left? Okay, with what is left, what is in that set. Oh, actually, I have to. I got it wrong. So this is not as simple as this. It actually gets a little bit more complicated. Let me get rid of this stuff here. Let me present a question first, and then we'll address that question. So I'll give you this question here. What is f of e? What is f of e? F of e is, okay, first of all, is it a set? Okay, that's the first question. From the outermost perspective, is f of e a set? If you just look at it, how it's defined, f of e is just a subproblem. In other words, it is also a set of outcomes, and each outcome is a combination, which means it is a set. So from that perspective, f of e itself is a set of sets. Okay, so it is a set of sets, where the set itself, f of e, is representing the set of outcomes, and each element of f of e is representing a unique outcome when you're looking at it from the perspective of you have only I minus 1 trials left, and the choices that you have to start with is everything in X except for element E. So I'm not seeing any questions in the text channel. Again, I think it can be a little bit confusing here. Alright, so now what we need to do is to say another for each. Okay, so this time we are iterating everything in f of e, because remember, f of e is a set of sets where each element itself is also a set. So we're gonna say, in this case, we use uppercase S as the name, and we're gonna, okay, just to make this more syntactically and also logically correct, we're going to use let here, which turns lowercase e and uppercase s into local variables with that scope. So let s of f of e do the following. So now in this loop here, let's revisit what we are looking at here. So e is the choice chosen for this ui of x iteration. Okay, that's what e is representing. The next question is, what is s representing? Uppercase S is one of the combinations of ui minus 1 of x minus the set of e itself. Okay, so this is what e is representing at this point of the program, and what s is representing at this point of the program. So then the question is, what are we supposed to do with this? Well, think about it this way. Okay, so once again, okay, if you are looking at this and go like, okay, this is too much for me to process because it's too symbolic, it's too abstract, then it is time to switch back to a concrete example. So the concrete example is you start with 1, 2, 3, 4, 5, and you only have 2 trials, right? So this is from the perspective of the top level logic. So we are basically saying each for let e of x is 1, 2, 3, 4, 5. And then each f of 1 is going to be asking, of 2, 3, 4, and 5, and only 1 trial left. How many? What are the combinations, possible combinations of that particular sub experiment, and so on. So from that perspective, now we have to say, oh, so if I use e as a part, as an element of s, that becomes a combination from the perspective of u of I of x. Okay, so I'm just going to say that first, and then we'll kind of talk about it. So we'll give it a local name first. Okay, so we'll say let combination. So we'll just say com here equals to s dot union with new set with only e as an element in it. So this syntax is for the most part correct, except for the method of union, which does not exist in JavaScript set implementation. And now, what do we do with com? Okay, because com is really a part of the result that we are trying to collect here. So now we say uix, which is what we are actually trying to figure out, is going to be uix dot union with com. So that is the recursive algorithm itself. Okay, so f of e is the recursive part. All right, so I'm gonna pause here and see if this is helping or not. This is me trying to explain, what is the process of coming up with this logic here. All right, cool, cool. Yep. F of 1 is the set of okay, so let's try to figure this out. Okay, so uix when I equals to 5. Okay, so we're gonna take a look at that specific example. Oh, I equals to 2, sorry, and we want x to be the set of 1, 2, 3, 4, 5. Okay, so we're gonna look. We'll follow the same algorithm, except in this case, we have a very specific or concrete example here. So x is that particular set. So in that case, we are going through this loop here. So we basically have one iteration when e equals to 1. And basically we have 5 iterations, right? Because e can be 1, 2, 3, 4, or 5. Now the question is, what if e equals to 1? What is f of e? Or f of 1 in this case. So f of 1 is basically looking at this definition here. Oh, okay, it's out of your view now. So f of e is this. Okay, let me move up first. There we go. So f of e is defined to be this thing here, which is we have one fewer iteration, one fewer trial, and whatever we chose as e is no longer available as a choice. So it's only x, but without that element. So given that is what f of e, let's go back to what we're trying to do here. So f of 1 is going to be, you have one trial left, okay, and the choices that you have left are 2, 3, 4, and 5. Okay, so what are the possible outcomes? Well, it's we can have 2, we can have 3, we can have 4, or we can have 5. Is that okay? I mean, that's exactly what Chris typed. Oh, not exactly as Chris typed, but this is the answer. Okay, when you have only one trial left, one is no longer available because we took one out for this particular trial. So the possible outcome when you have one trial left and the choices available to the first trial is 2, 3, 4, or 5 as a set, you have only 4 possibilities, right? Here's a bag I give you. There are 4 marbles in it. You are allowed to take 1 marble out of it. So how many ways can you choose 1 marble out of 4? Exactly 4 ways, right? So that's why the outcome is like this. Are we doing okay so far with the concrete example? All right. All right, cool. All right, so now you can probably imagine what the other ones are going to look like, right? Okay, so f of 2 means 2 is no longer available as one of the choices, but the other 4 things are available. So that means 1 is available, 3, 4, and 5. Okay, so you can kind of imagine what these are going to look like. So 3 means 3 is no longer available, but everything else is. So I'm just going to finish this like so. This is 4, and 3 is now available, and finally we have, oops, this is 5, and now we have that. Okay, now what do we do? Now that we know what is e and what is f of e, now we have to look at this and go like, okay, so what are we looking at here when we look at s here? So there are 4 possible ways for s to end up with, because remember, s here is an element of f of e. So when we look at this specific concrete case, there are 4 iterations that we have to go through. The first one is when s is the set of 2, and the second one is when s is the set of 3, this s is the set of 4, and S is the set of 5. It's actually it's actually really bad. It's not exactly Cartesian product. It has a similar feel to it, except it is without replacement. That without replacement part makes things a lot harder. Okay, so we are now looking at the this iteration. Okay, when we're looking at the case where we say for each s of f of e, do the following. So now we can now figure out for each of these iterations what's going to happen. So now we say, what is COM? Okay, COM is basically the union between S and the singleton set that consists of E itself. So I'm just going to write out, what it's going to look like. So it's the set of 2 unioned with the set of with only E in it. Okay, so now, but since we know what E is, right? Because the indentation indicates all of these are cases. This is what happens when E equals to 1. So we know what that is. So COM in this case is just 1, 2 as a set. And in the second case, I mean, you guys can probably figure this out. This is just when COM is going to be the set of 1, 3. And this is the set when we have 1, 4. And this is the set. COM is when the union between S and the singleton set that only has E as an element is 1, 5. Are we still doing okay so far in terms of understanding what each COM is going to look like in the algorithm? And the algorithm is up here. This is just me trying to figure out what COM is. All right. Alright, so we also want to track UIX, right? UIX was an empty set to begin with. So UIX is just an empty set to begin with. So after this COM here, UIX is unioned with COM. So that means, oh, I think I made a mistake here. It is not unioned with COM. It is unioned with the single set of COM. So I have to change this code here. Okay, this is me making a mistake. Sorry about that. So COM is an element in a set, and we are adding that as an element into UIX. Now let me go back to the algorithm here to basically say what. See this extra braces over here? That's what it is. Okay, we are turning the set that is the union between E and S into a set itself, and that is being considered as an element to be unioned by this thing over here. So that's that's one extra level of union here, because without the extra braces here, then we'll just union everything. We just end up with 1, 2, 3, 4, 5. But with this extra union, with this extra pair of braces, we end up with elements that we are just adding into a union. Okay, so getting back to my notes here. I have no idea whether this is really helping or not, but I'll continue to try. So in this case, UIX at this point is going to be a set that has another set in it with only 1, 2 in it. Are we still doing okay here? Because of the change that when we are unioning, we are actually creating a new element, where the element itself is a set. Are we still doing okay with that part? All right. Cool. All right. So I am really tracking everything down. Okay, Chris and I were just talking about how in one of his classes that he's taking, the professor also likes to kind of track everything down. Well, in this case, I think it's helpful to track it down. So now the question is, do we have a duplicate element? The answer is no, we do not have a duplicate element, because 1, 2, and 1, 3 are distinct. These two are not the same element. In fact, if we keep doing it like this, 1, 4 is also not the same as any other elements in UIX. And then finally with this one, it's kind of same deal. So 1, 5 is also its own element. So you guys might be asking, so why do we have to do the union thing and we just, it should be a whole lot easier than this? Well, it's not. All right, so now we move on to the second iteration where e equals to 2, and you guys are probably thinking, oh no, we're going to do exactly the same thing, the same tedious stuff here, and the answer is yes, we are. So we basically iterate through every element of f of 2, and in each iteration, the variable holding the value for that iteration is uppercase S. So in this case, we have 1, 3, 1, 3, 4, 5. Okay. Now I do have to go through this part here because this is going to make it clear why we need to do the union thing instead of using a tuple. All right, so now we can look at this and go like, oh, okay, what is COM? Okay, so COM here is basically, let's go back to the original definition of what COM is. Okay, because when we have questions, we want to look at it. So COM is the union between S and the singleton set consisting of E itself. Okay, so that's not too hard. So in this case, we have 1 union with E, and E is right here, right? This is E, and S is the set of 1, and the 2 union. Okay, let me just kind of spell the whole thing. US union with the set with only E in it. But in this case, it becomes the set of 1 union with the set of 2, which then becomes the set of 1, 2. The next step is now really important, because what is EIX at this point? UIX, sorry. So what is UIX at this point? This is what UIX already looks like. And we are trying to say, we are just trying to add or union this with the set that has 1, 2 in it. So now the question is, yeah, we have some concrete work going on, so it might get a little bit noisy in the background. Not much I can do about that. Alright, so but this is really important because the importance of illustrating this step here is to say, but 1, 2 is already in here, so we are not going to double count it. That is the important part. Exactly. So what Chris wrote in the text channel is exactly what is happening here. So we're going to apply the same thing, to the case when S equals to 3. So now, what is COM? COM, I'm just going to, kind of shortcut the whole thing. So COM is whatever S has, which is a 3, combined with whatever E is, which is a 2. So whether you write it as 3, 2, or 2, 3 does not matter, because in a set, ordering is not important, within the listing of elements in a set. So I'll just keep it like this. But what about UIX then? So now we look at, okay, I'm going to copy this one here, over here. And this time what we're unioning is not 1, 2 anymore, it is 2 and 3. So what is the result? Well, 2, 3 turns out not to be in the set already, right? It's not on this side. So when we union these two, we actually end up with 2, 3 being added to the original set, like so. And so on. So do you guys, I mean, I don't really want to finish this because it's kind of tedious, but are you guys starting to get the idea of how this works? All right. Now, to me, whether you can follow the algorithm is one thing, but what I really want to teach is how to formulate the recursive definition, because that part is, to me, a lot more important, because if I just want you guys to follow the algorithm, the pseudocode or whatnot, I think JavaScript can do a better job than any one of you or myself, right? Because that's what computers are for. What I want to really teach here, or what I want you guys to pay attention to, is how to look at the problem, how to figure out that, hey, this bigger problem can be broken up into smaller steps, where a part of each step involves trying to solve the same kind of problem, except the problem is a little bit smaller. That is the important part that I want to illustrate. Even though the mechanical aspect of this, whole thing is kind of distracting, but the concept of how to develop, how to write your own recursive algorithm is much more important to me. Are we still doing okay so far, or do we have any questions regarding the tracing of this algorithm? No questions? All right. So, do you guys still want me to kind of quickly go through this entire thing? Because I probably can. So this is just 2.4, and then UIX, 2.4 is going to be new to this whole thing, right? So we'll have 2.4 over here. Yeah, I can do that. And then, for this iteration, com is going to be 2.5, which is also new to UIX. So UIX ends up with 2.5 in it. And then we move on to when e equals to 3. Okay, so the indentation level, in this demonstration illustrates the nesting of the logic as well. So I think that part is really important as well. Oh. Chris just put some shiny object into the off-topic channel, and I go like, oh, I want to know. I have to stop. No, let's not do that. All right, so in this case, S is going to be 1, 2, 4, 5. Okay. And I'm going to finish like some additional steps, but then I'll let you guys finish the rest. Okay, it's not going to be for grade, but I think it might help you understand the algorithm a little bit more. Just because you're going to go through, you're going to follow the steps and go like, okay, so we just have to figure out what this is. So in this case, it's just 1, 3. Now this is important, because are we adding 1, 3 to the set? The answer is no, because 1, 3 is already here. So that means, the more you have progressed through this algorithm, the less likely you're going to be adding new stuff into UIX, because you're going to end up with some duplicate elements or duplicate things that are generated. So the duplicate things will just be merged without duplication into the solution. What about the next one, 2, 3? Well, as it turns out, 2, 3 is also in the set already. So even though the next one is 2, 3, but you can see how 2, 3 is also in the set already. What about the next one? Next one is 3, 4. So 3, 4 is new. So we're going to have to add that one to the set, because this time we have 2, 4. Oh, I take it back. It's 3, 4. So it's a 3 and then a 4. And that's new because we have not, we do not have a set of 3, 4 yet. So 3, 4 is going to be added. All right, so I think the rest you can probably just kind of go through the whole thing and work it out. So is that okay? Does everybody kind of get a better understanding of the recursive definition and how it works, and also, at least a little bit of the rationale of how it was developed from the, in the beginning? This is actually me trying to explain my thinking process, which of course is going to be very difficult to test whether you can follow that or not, because after all, my thinking process is here, and it's not possible exactly to explain everything in my own thinking process, but I will try my best. All right. How many of you are taking CISP430 in the same semester, like now, in this semester? Because if you are probably going to have to write some recursive algorithms, and I'm hoping that this might help you, to kind of address some of those recursive algorithms too, because the the way you think about recursive algorithms is important. Okay, how do you approach the thing? How do I break a bigger problem into smaller problems, where each smaller problem has at least a component that looks like the problem that we are trying to solve, except it is smaller. And that's the way we look at recursive algorithms. How are those diagrams treating you? I don't know what you guys are talking about, but I personally do not like diagrams. I know a lot of people like diagrams, but I don't. All right, so now with the U function, kind of explained, I want to leave it up to you guys to look at section 6, because section 6 is about permutation, which means ordering is important. So we are dealing with tuples. Okay, so we're using tuples to represent a single outcome of an experiment, as opposed to using a set to represent a single outcome of the experiment. But the concept is very much similar. Okay, so the way we think about this is going to be about the same. We start with the base case, which is basically saying, what if we are looking at 0 trials? So when we're dealing with 0 trials, this is how it's defined right here. And you can see it looks almost the same thing as u0 of x. Okay, yes, I use t instead of x here, but that's just a name change of the parameter. But instead of using an empty set as the only element in the set of outcomes, the outcome itself is now a empty tuple as opposed to an empty set. Now that becomes really important, because the way we combine is no longer formulating a union. The way we're combining is now using a Cartesian product. So that is a little bit different, but in terms of the nesting of the logic, and also in terms of the recursive nature, which is using, let me go down here, which is using a recursive definition of omega in this case, that part is very much similar. In other words, the rationale of how I came up with these two algorithms were almost identical. They are very, very close. The only difference is, how do we combine the solutions of the subproblems to a part of the problem that I'm trying to solve now? One is done through using union, and the other one is done through using Cartesian product. We are running out of time. Obviously, I don't have time to trace through the algorithm in section 6, but I want you guys to kind of think about it and give yourself the example. Same thing. Well, actually, you might want to give yourself a simpler example, because the number of permutations of 5 choose 4 is a little bit more hairy compared to the number of combinations of 5 choose 2. Sorry, 5 choose 2, not 5 choose 4. So you might want to reduce the problems to say 3 choose 2, in terms of permutation, because otherwise you're going to end up with spending a lot of time with all the tedious stuff. So just kind of reduce the size of the problem, but use a very similar way to kind of trace through the algorithm. So this way you have you can relate a concrete example, going through the logic, and trying to understand the algorithm to find out how it works. Yes, I'm not taking roll anymore, as I explained earlier in the class, because I cannot drop people because of lack of attendance anymore. So I think at this point of time, whether people attend the classes or not is really not my problem. So I'm not taking rolls anymore. All right, so we are done with today's lecture. No, I don't have a problem with anyone continuing in this class or not. I mean, this is definitely each person's choice. So I'm still gonna grade the exam the same way, which is taking a little bit too long. But so I will post the notes here so that you guys can at least finish with this one. But if you can kind of do something similar to this, but with the algorithm in section 6, I think that would be great if you can do that before Wednesday. Because on Wednesday, I'm hoping that we can move on. Let me just kind of present what we'll be talking about on Wednesday. So on Wednesday, we are going to move on to talk about discrete probability. And I'm going to give you a quick, kind of preview of what this is about. So this one talks about the birthday problem that we have already talked about, but the most important part of the next module, which is hopefully what we're going to be able to get to on Wednesday, would be Pascal's identity, the binomial theorem, and also the concept of proof by induction. So hopefully we can get to proof by induction because it is also a very powerful way to prove theorems. And this one is particularly helpful when you are doing computer science stuff like algorithms and whatnot. All right, so I am done with talking in lecture today. If there are any questions, you can go ahead and post it, and I can try to answer those questions as quickly as possible. If not, I'm gonna get out of the voice channel and we'll correspond with text. All right, nothing here. All right, so I'll see you guys on Wednesday. And don't forget to try to kind of follow through with the exercise. I will post the notes here. Yep, all right. Everybody have a good rest of Monday.